Baldwin. Okay. We'll give a minute because it's 11:43, just to make sure that we start on time for people to join. And then I'll introduce. Okay. So it's 11:45 Central Time. So we're going to get started with our next talk. The title for this talk is on grid control theory and resilient control by Dr. Tom Baldwin, undergraduate program director at Idaho State University. Tom received the B.S.E. and M.S.E.E degrees from Clemson University, Clemson in 1987 and 89. And a Ph.D. in electrical engineering from Virginia Polytechnic Institute and State University, Blacksburg in 1993. Dr. Baldwin is currently a professor of electrical and computer engineering at Idaho State University. In addition, he runs an engineering consulting business focused on electrical power systems and industrial controls, and is an adjunct professor at Brigham Young University, Idaho, and University of Idaho, teaching electrical power systems. Prior to joining ISU in 2015, he worked as a power system specialist at INL and a professor for electrical and computer engineering at Florida State University. At FSU, he was an associate director for the Center for Advanced Power Systems and conducted research in support of the Office of Naval Research. He has also worked at ABB Electric Systems Technology Institute as a senior power systems engineer at M.S.E.E. Haynes Corporation as a design engineer, and at Birmingham Technologies as a research and design engineer. Dr. Baldwin's research and engineering design specialization include power distribution system design, industrial power system design, fault analysis and arc flash in industrial power systems, grounding system design and troubleshooting, medium power transformer design and applications, analysis of power quality problems, solar PV and wind energy systems, ICS, and computer-based distributed control systems. Dr. Baldwin is a registered professional engineer in the states of Idaho and North Carolina. He is a fellow member of the IEEE and a member of the IEEE Power and Energy and IEEE Industrial Application Societies, and serves on several committees and working groups. Dr. Tom, it is our pleasure and distinct honor to invite you for this workshop, and I appreciate your spending your time this afternoon here. And the floor is yours. And can you hear us?
Yes, I can. Okay, let's see if I can share my screen.
Yes. Yes, we can see your screen. Yeah.
Very good. So Brian has done an excellent job at laying the groundwork. I'm going to be adding upon what he has presented. a little more detail in the grid control side of things. We'll talk about theory and control laws, and hopefully gives you the foundation towards resilient controls, which will be in further discussions later in the afternoon. Let's see if I can get focused now. Yes. And just continuing on some of the words that Brian has already mentioned to us this morning. The utilities have always strived to aim for certain levels of resiliency, definitely in the areas of reliability and economics and things of that nature. But some other things I'd like to point out in the way utilities try to spread out risk that are always involved in the production of electrical energy. One of the primary things that we have to do is diversification of all the various resources. And this includes all the way back to the power plants, choosing in any given utility more than one source of energy conversion into electricity. And we've had discussions on thermal systems, which also include fossil fuel, nuclear, burning of coal, natural gas, things of that nature. Nuclear has been an important member of keeping base generation going for many utilities. Something that has had different types of risk over the years, and unfortunately, Fukushima and Chernobyl and 3 Mile Island each continue to put a smudge mark on nuclear power generation, keeping us from moving forward. With the growth of small modular reactors and repeatable designs in the nuclear industry, we're hoping that this will continue to move forward, and we hope to see new nuclear power plants being built into the future. Hydropower, Brian has also discussed, run of the river, as well as impounding of water resources in pump hydro. The challenge is there. We could try to build more hydro facilities. The good spots for building hydro, for the most part, have been identified and have been utilized, or unfortunately, they exist in locations where sensitivity in other aspects of human society has caused that the construction of dams are not going to take place. And there's, of course, the challenges of all of our power conversion in the fact that anytime that you do energy conversion, there's always some consequences of that conversion, whether it affects climate or it harms vegetation and wildlife. Wherever we have our systems, there are always consequences that take place. And that also includes solar and wind as well. We'd like to see renewables continue to grow. We do see the problems that are associated there. In fact, that just to repeat that, in essence, we treat them as negative load because of their dynamics and difficulty to predict moment by moment exactly how much energy is going to be available from those resources. Geothermal is another important one, and it always seems like where good thermal sources are, we also tend to have national and heritage parks where geysers and other wonders of geothermal activities taking place tend to also be popular places for recreation and amusement to watch the geothermal actions take place. One of the other key aspects is geographical distribution. The talk about putting generation closer back into cities, like it was at the very beginning in the mid-1800s, is being a renewed effort. Do you want to try to get generation distributed and closer to the various load centers so that, again, when disturbances and events take place, that it's easier to rebalance the system as different parts of the system must be shut down and restarted. If we look over in the transmission, we've talked about before the need of a mesh grid arrangement where power has multiple pathways to flow between generation sources to load centers. Always has been done at the transmission level for the most part, and we've seen that grow through the years. Brian gave us a good history of how in the 20th century, utilities went from isolated utilities to interconnected utilities in order to increase reliability and sharing of generation resources. One of the primary benefits of interconnecting the utilities is across the tie lines is to share emergency reserves. And we talked about spinning reserves and capacity reserves. These can be very expensive, and sharing the responsibilities across several utilities with the difference between what the current utilization rate at generators are versus their maximum power output gives a lot of little pieces of reserves that can be added up to represent a very large reserve, and taking advantage of the statistics that doesn't have to be shared by or that can be shared by everybody but doesn't get utilized except for a very few that run into a condition in which there has been a failure of some part of either a major transmission line or a generation power plant has gone down. Of course, the risks were also demonstrated in this, that the more complicated the system, the likelihood of cascading outages begin to take place, and the control system becomes ever more complicated. Controls have always been a major part of the electric utility system. And at the very simplest levels, very basic local controls have been seen in network protection, where in essence, electromechanical computers being replaced by electronics and then intelligent and electronic devices of embedded processors have always provided logic to identify a problem, not just a fault on the system, but other types of problems, and determine if there is a action that must be taken place, primarily the operation of a circuit breaker, and deciding which circuit breakers need to be operated to isolate the cause of that particular problem. Logic is also there as we improved the technology to provide reclosing, so that to remove the human operator at times when a fault has occurred, and many faults tend to be momentary faults. So the idea comes about to have the circuit automatically reclose and try the circuit out to see if the temporary fault has dissipated. Lightning flashovers is a classical example of that, or a tree limb blown into a power line, but as the wind subsides, the limb returns back to its original position. Those represent momentary, temporary faults that reclosers operations are able to quickly put the line back into service. Again, this improves reliability, but not necessarily resiliency. Power plant controls, generators we've talked about. We're going to talk a little more about that this morning, get into some of the details, and the fact that there's two levels or two areas that we're controlling: the real power delivery, as well as supporting the voltage that leaves the power plant. Real power is tied to frequency, and so we can use the frequency of the system to measure the balance of power. And voltage and reactive power are highly coupled together. And again, we can then try to address the need to take care of reactive power in a local sense to take care of the inductance that is normally found in the system, and make sure that either we're absorbing or producing the right amount of reactive power through voltage control to make sure each part of the system is operating correctly, and maintain the need to provide voltage at the customer's end within expected tolerance as given in specifications by standards. Power plants are usually the primary control points for the transmission system. At the distribution level, the distribution substation becomes that control as we break the system up into different areas and provide different levels of control. At the substation, voltage control is important, both with capacitor banks, but important is voltage regulators, and you often find other pieces of equipment there. Online tap changing transformers, which is very similar but slightly different than voltage regulators, which depends on where the voltage problem happens to be and at what level of controllability you want to have it at. Static VAR compensators and StatCons are electronic versions of this. When we have loops in the system, either transmission level or at the interconnection points, even in distribution, power flow control becomes necessary. And one of the primary tools we have is phase shifting transformers in the traditional sense, and flexible transmission lines with electronic components form the other component of that. In all of this, primarily design objective is the balance of power while keeping a certain amount of resources in reserve for contingencies. And so what this speaks of is the fact that in transmission and distribution and generation and all these levels, not all the resources are used to their fullest extent. We must maintain certain margins in order to allow for events to take place that we were not expecting, and those resources can then be fully utilized without causing overloads and damage to the network condition. So let's talk about some of the grid control points. For the power plant, the output power is the primary control point. Voltage follows along with that. Addition to that, the power plant itself has its own operations. It's no different than any manufacturing plant. Its product of that output is the production of electricity. And so all the normal plant controls that you would see in any manufacturing facility, especially looking like a chemical processing plant, you would find in a power plant. And so therefore, we won't get into those discussions, but that's very similar to any type of industrial level controls where you're running feed pumps, conveyor belts of coal, scrubbers for pollution control, monitoring of data points all over the place of temperature and pressures of steam, just like any industrial power plant. And so there's really in the control room two controls. One is the plant control for providing the prime mover, the rotating shaft to go to the generator. And then there's the power controls from the generator connected to the grid. So our voltage, excitation, and our governor are all there on the second level of control. In substations, we have our grid controls so that we can effectively make sure that power is flowing in the right direction with the correct reactive power compensation for us to run efficiently, and network protection in the background, constantly monitoring, hopefully used rarely, to take care of abnormal events and making decisions on how we are going to correct those events. This includes non-fault events, and so this would be things like watching for swings in the power system. So one of the things that can occur is anytime that you have a change in loading or a disturbance that takes place, resources are temporarily lost, then generation has to reroute power to the load. And if that is not successful for a moment in time, energy can be built up in the generator rotating masses. And once power is able to go back to the load, we have the problem of that excess energy stored in the rotating masses and also seen as changes in frequency. And so as the system over matters of seconds to maybe 30 seconds, the system will begin to swing in generator output, and the amount of power that is shared between the generators. So some generators will feel a motoring action taking place where power is backflowing from overexcited generators into, or overspeeding generators into undersped generators, and we can see this system swing. And this is normal as long as the swings dampen out. But if those swings do not dampen out, network protection is there to break the system apart at key pre-identified locations, so as the system can island momentarily to maintain system stability. Many of these actually occur across tie lines between utilities, but tie lines are there primarily for such emergencies, so loss of a generator, and powers can then flow across the tie lines to support a utility that has lost a resource. And other utilities are in a compact to provide services to maintain energy and generation resources to make up the momentary loss of a utility's generation. It also helps in providing regional stability. Now, tie lines can be both good and evil. We saw in the 2003 blackout, for example, where the tie lines were overstressed and caused cascading outages between utilities. But on the other hand, American Electric Power recognized what was going on and isolated the cascading by opening up its tie lines and preventing the disturbance from heading further south and west of the Northeast area. So the balance of power is important at various levels in the system. And so we have our basic equation here that defines the balance of power. So all generation power in a system must equal the power being exported in or out via the tie lines to other utilities. And the generation and tie lines take care of the load power and any losses that are take place in the system due to the resistive loss of conductors and corona. Now, the tie lines have also provided the ability to buy and sell power. So the marketplace now becomes an important part of utility operations. And so we have the wheeling of power. A wheeling term is commonly used in the marketplace of moving power across large regions of utilities. And contractual arrangements are made. That's because in different parts of the country or the world, the generation of electricity is cheaper, perhaps in one area at one particular time. Their fuel costs are lower. So they may be in the opportunity to sell electricity to other utilities whose generation is more expensive. And so they might want to purchase power from the low-cost generation providers to ensure that they run most economically. The behind the scenes of what we've talked about so far, economic operation of the utility is just as important, and it folds into the controls of a power system. So optimal generation dispatch is a set of programs that run on the SCADA system, taking into effect historical data and these short-term load prediction for that day and for that particular hour of the day, and try to determine how much power generation is going to be needed, and give the set points to generators as to which generators should be operating for the lowest possible cost of operation. And so they give input to the control systems as to the set points of our generation power output. Now, what's important is that it runs through a short-term load prediction, which uses both current data of weather and other events that are taking place on it for that particular day, and takes into effect the historical data of how much power was used the day before, or what was used in the years past, and under what weather and other conditions are taking place. So historical data and current data are mixed together to come up with a prediction of how much power is going to be consumed by customers for the next 30 or 60 minutes. And under those constraints, what should the distribution of loading across the generators be? Or in other words, what should the set points of the output power of generators ought to be to run the system efficiently? But this also is biased because at the same time in the energy management system, an optimal for contingency analysis is taking place, and to find the right operating point of the system. So contingency analysis, again, looks at making the system survivable after events taking place. So we look at the loss of one or two major pieces of equipment, and if that should occur, what should the operating point be of the system such that the system remains stable and in a place that the operators can continue to work short term till resources are restored or new resources are made available. So the objective there is you don't want to run a system so economically that if an event took place that you would not have the right additional resources necessarily to keep the system in operation. So embedded in this is the spinning reserves and power margins that are necessary to keep the system operating with the loss of one or two major pieces of equipment. And it is a challenging piece of software that is taking place, trying to find an operating point amongst all the different types of outages that could take place. So each of the generators is looked at. If it went offline, how would that impact the operating point? Or what if a major transmission line was to drop offline? So all these are taken into account and have to be done very quickly so that that information can be used to adjust the generation operating levels. In abnormal operations, we experience that by having either loss of generation, loss of transmission or transformer, or any of our auxiliary pieces of equipment. Equipment does age, it does fail. Weather events and other outside events take place that cause failures to occur. And those are amongst the physical failures. We do experience a number of control failures. We've talked about a little bit about network protection. Misoperation of relays is not uncommon. It does occur on a regular basis. That's a study amongst the relay committee members in various organizations to try to root out how to get rid of incorrect set points in network protection. Sensory measurement errors are always taking place. Instrumentation becomes uncalibrated over time. Equipment does age and fault out. And so sensory errors are always a common problem. And this gets elevated because that data is being collected across the system and being fed back to the energy management control system. And so to accommodate that, we have state estimation that takes place, and we'll talk about that in a second. There's also data errors in our communication network and data failures. One of the things that drove historically the use of local controls throughout the utility was the fact that communication networks were just as unreliable as the power grid itself. And so decisions needed to be made without relying heavily on communications. And as improvements have been made over the years, communication networks have become extremely reliable. And so we have tied together and merged together the concepts that use communication data of distant events, distant sensory information as much as you want, but balance that with local control that's able to make decisions, especially if that data coming in is corrupt or unavailable. SCADA systems play an important role here, but they do have software errors. We've seen utilities like First Energy and others who had problems with their SCADA system software that caused events to take place. And inside of those, SCADA is one of the most important parts of collecting data, but collecting data needs to be reviewed for its accuracy so that a state of the system can be presented to the energy management system. And so we have state estimation, whose whole objective is to use a model of the utility grid and use the sensor data collected at over many parts of the grid and check to make sure that the data is consistent. State estimation, if done correctly, should be able to identify bad pieces of information and flag that and remove extremist pieces of data errors. On the other hand, it can help reduce the sensitivity to normal measurement errors that always take place in equipment as calibration drifts over time. State estimation has had the challenges that it has been static in nature and taken on samplings on the order of 15 minutes to maybe even 30 minutes, so it only gives you a snapshot of the system. But that's changing as resources in communication sensors, as well as software and computing systems have improved. The recovery after an event is important just as well. And this is where humans really come into the loop. System restoration and identifying of key resources that are still available, what can be put back into service quickly, how to stabilize the system, where are we reaching limits that might create cascading events, what actions need to be taken place quickly to bring the system into a more stable operating point, how do we get equipment back online, restoration of generation, recovery of generation, bring it back in online if possible, minimizing the outage area, and over time making the repairs in the outage area and restoring power back. Some of this is automated, a lot of this is human in the loop, and so recovery is an important piece of the puzzle. The threats have always been known at some level: weather, events, animals and vegetation, human and equipment accidents. It is surprising the number of errors that take place due to human factors, and that will be a discussion later on. Equipment failures take place, as we've talked about before, as equipment is aged or overloaded and weakens the equipment. But there's also new threats that have shown up over the years. Threats from theft and vandalism have taken place. Substation attacks. Cyber attacks have become ever more so. Things that are not necessarily totally obvious. Information theft is very important. If you are able to crack into the SCADA system, know what the state estimation model is, that gives you a tremendous amount of information about how the system sees itself. And you can use that information to form attacks. So keeping your information secure is extremely important. There are the abilities to attack the data coming in from the sensors. If you can insert false pieces of information about how the system is operating, and you do it judiciously such that you overcome the state estimator rejecting that data, you could then fool the system and the operators that the system is in a state that it really is not in, and hence improper control actions being taken place. And likewise, on the other side, control signals going out between the centralized control center to the power plants and to the generators, telling them to operate in a different mode than what was intended by the operators. There's also the most famous overtaking of equipment, especially at the substation level, and either changing its functionality or denying the functionality, locking the equipment up such that protective relays do not operate, or you've opened up circuit breakers and turned off the programmable logic controllers that allow them to be controlled remotely by the operators. Ukraine has seen a lot of those type of attacks from attack players going in and and willing cyber attacks on the various pieces of substation equipment. Then there's always the problems of disgruntled employees or community members. Nothing worse than having the internal threat of people who know the system and sabotage it. But then there's also the carelessness and senseless behaviors and pranks that are also played upon the utility control systems and infrastructure and equipment that just cause mayhem in general. Power plant controls. We've talked about that. There's two basically major controls: the internal plant controls for the overall operation of making sure the prime mover is moving, and the classical controls to the control center so that output power can be maintained at given levels. And so part of the classical grid controls is to maintain that the system is operating at frequency, whether 50 or 60 hertz, and make sure that the output voltage is at the prescribed level so that we have proper voltage throughout the grid. Substation controls. Most substations now become automated and unmanned. There are a few that do have humans nearby at very critical substations. Remembering that our primary functions of substation is voltage maintaining, distributing voltage levels to the various parts of the system, providing fault protection. Control points are transformers, tap changers, voltage regulator controls, operating of auxiliary equipment like circuit or the capacitor bank sections, operating those switches, the intelligent electronic devices and the protective relays are responsible for carrying out these operations. A number of PLCs are found in this area to automate sequential operations of events. Then the other important matter of substation is it's a major point of data collection where we monitor power flows, currents levels, voltage values, and sending them back to the SCADA system. But also very important is the status of circuit breakers and tap changers on transformers, what are their current positions. That data goes back into the SCADA to the state estimator so that we have a good vision of what the state of the system is and having a good system model. Utility Control Center is the brains of the utility. Inside there are a number of redundant computer systems and operator stations. The energy management system and the SCADA system are running on those computers. So we have the state estimator running the optimal power flow, contingency analysis, and as necessary, operators can use load flow and fault analysis to make predictions about what's going to happen with the current system. Also very important is our performance indices are determined for the system based on the state estimation data and provided to the operators so that they know if they're meeting performance targets. The other major portion of the control center is the collection point of data recording. So all events are recorded and so that post-mortem analysis can occur later on. Control centers are also important in the fact that they are the points for the local utility to transaction with the bigger marketplace for buying and selling electricity between utilities and regions. And also this is the place where ties to the higher balancing authority. So information is fed up to the NERC authorities such as the independent system operator or the OASIS for the utility NERC regions. So if we look at it from a structural standpoint, we have a number of different systems going on. At the utility level, we have the distribution management system, similar to the control center for the transmission level, the energy management system for transmission with SCADA, databases of collecting the various pieces of data, historical data as well as current data, our front-end processors of collecting data from the field, the communications back and forth of control signals as well as sensor signals, our substation remote terminal units that interface to the various relays and controls for our transformers and capacitor banks, and hence all the field devices that are throughout the substations that provide this service for us. So the control objective of our generation is provide 60 hertz or 50 hertz power as specified by each different areas, maintain voltage, and to drive the area control area for a utility to 0. This is our balancing rule. We have control laws for making adjustments when we have too high or too low frequency. So over frequency and positive area control area or error basically says we have too much power. And so we must reduce what we're delivering from the prime mover of the power plant to the generator. And so we'll control the set point of the governor down. Another control law is if we have under frequency and negative area control errors. And so that means we don't have enough power being generated. And so we increase the set point on the generator to provide more power and more speed. The real challenge comes when we have mixtures such as over frequency and negative area control errors, or vice versa, under frequency and positive area control errors. And in this, we have to weigh in the various components to find out which direction we need to take the generators. Now, the generator general set points are what we would wish to have the generators operate, and that's coming from our economic dispatch and optimal power flows for our voltage and power output, as well as our area control errors, which are generated by the SCADA system. So these form the inputs then into our control loop. The feedback loops that take place is that we do measure the speed off the shaft and take that back to the governor. And so that will then either adjust the steam valves or the penstock gates for hydro. The excitation then controls the voltage output of our generators, and we measure the voltage to make sure it's within the values that we want the generator to operate at. So we have 2 feedback loops that occur there inside the plant. Then we have protection that's built around the generator. And so the primary one there is, from a control standpoint, is the power system stabilizer. So if we've had a major event take place and it gets cleared, we're now concerned that the system swings, the dynamics of it take place successfully. Now, this could occur either because of a fault, or it could occur just because a large set of customers come online or shut off quickly, and so they can introduce load transients into the system and causing the system to swing. Other protections are classical, such as generation protection, to make sure that the generator is operating properly, or that events that occur just outside the power plant are also addressed if the generator has to be shut down. Here's a classical view of the control systems around a generator. And so we've just talked about those. And here's some details that are done at the educational level, modeling the various control systems so that one can begin to put these things together and have practice with them. And so we want to make sure that you have some basic tools. These are great to put into analysis programs such as MATLAB that you can then simulate various generating events. The governor has a droop type control. There's a similar one also for voltage regulation, so that effectively, as more power is needed in the system, we see that being drawn from the inertial masses of the generator and causing the speed to droop and indicating to the governor that we need more power. And likewise, we do this with voltage drops and to improve our voltage excitation. So there are parallels of both power and voltage in the control system. Basic generator controls, we put these things together. This is quite appropriate from everything from a standby generator inside a industrial facility all the way up to a single generation utility. Great for you have a set point that you want to control, make sure you have a right frequency, and as loads change, the generator and its governor are able to respond. Of course, what becomes more challenging is when we start to put together multiple generators. And one of the key points there is how they share load between the generators. And equally well, using set points of voltage so that reactive power can be shared between generators as well. And so what we now do is add to the system the effect of how much power is being produced by different parts of the system, as well as how the frequency is changing in the system. And so we take frequency measurements and feed that back to our system. Then we get to the level of providing area control error, where now these are the inputs from not only our proper operation of our generators to maintain frequency, but also maintain our contractual arrangements of how much power should be flowing across tie lines and making sure that our balancing authority is meeting its contractual arrangements through the area control error, and that tied with our maintaining of frequencies for proper generator output to run percentage-wise, to run economically. All those are put into balance with a control system this way. Take a quick example. We have a two-generator system, connect our two generators and two systems tied together by a tie line, and we have some generator parameters there. What happens if a 10 megawatt load change takes place in area number 1? We can then take a look at what happens to the swings in the area. We see that the onset of the load will cause a shift in power and take that power out of the rotating masses. It senses this, the system senses this by changes in frequency within both areas. Both areas try to respond. Area number 2 actually, we have a change. Area number 1 gets 10% or 10 megawatts more power. Area number 2 dampens out, and the frequency and dampens out, and the tie line power returns back to its normal level of operation. Now, over time, we have continually tried to improve the resiliency of the power plant and the system control center and the grid. This has always been a work in practice. We've primarily focused on reliability initially, but as reliability has improved, other areas of improved operational controls have taken place. And we can see these in the advancements of certain technologies. In the 1990s, synchro phaser measurements became available. One of the things that this did for the industry, with the help of Schweitzer's engineering labs to come up with improved relays, it allows us direct measurements of voltage and current phase angles. And this has led the way towards eventually, hopefully, implementing dynamic state estimation. And with dynamic state estimation, we basically start speeding up the time rates at which state estimation is being performed, give much better conditions of the state of our system, and as well as modeling the dynamics of the system and coming up with the dynamic parameters, this dynamic state of vectors for our system. This still is a work of great importance that is in the research areas where we haven't gotten this to a commercial state yet. But that's been an important goal for the industry. The other side of this is we've seen over time with better communications, the integrating of circuit breaker status with our state estimation so that we have much better modeling with better data coming in from the remote areas. Real-time digital simulation has taken place in the turn of the century. So the 21st century has seen the growth of real-time digital simulation. The goal here is providing the digital twin. Can the system have a digital twin completely in simulating the current operations of the system? And so this gives us the ability then to make a one-to-one comparison. And this has been accomplished by having faster than real-time calculations of the system dynamics. Still work of research to perfect this, but this would greatly provide information to the utilities by being able to compare existing operations with the digital twin and seeing how the two are differ and what's causing that difference to take place. One of the other areas that INL has worked on for a number of years is the scalability of the control areas. So transmission with this generation in most utilities has been done pretty well, but we want to take these capabilities at that level and move them up and down the various scales. And so microgrids has performed this at one level, taking distribution and trying to overcome the cost of trying to add these type of resources. But distribution systems could greatly benefit by having distribution level energy management systems and control areas like occurs at the transmission level, even down to users level, and then all the way up to large interconnected systems. The sharing of things such as energy storage and remote generation as well as local generation, so that the system can then break apart and operate as independently as possible when necessary, but together share resources and work together in the large sense. Now, distribution systems is an area that needs great work done. That's because distribution systems, for the most part, except for cities that could afford to go into mesh operations, radio distribution systems are great for minimizing cost and having very little control capabilities. But network faults have caused us to rethink that, because when you lose a great part of the system because you have little resources available to it, invite opportunities to put in microgrids, local generation resources, and better controls then of the distribution system. So many utilities aren't quite ready to jump completely into a mesh type distribution network, but we can take incremental steps in closing loops in the system so that we can have loops that can be managed. Right now, there are some loops that are built into the system. We can take advantage of that, but those loops stay open, normally open state, and are only closed in if the part of another distribution section has lost service, and we can backfeed power into those. We'll show an example of that in just a second. Many of these have been hand operated by operators, actually linemen out in the field. The goal is to make this remote controlled, but now based with much better intelligence. So here we show a basic set of distribution networks, different neighborhoods, for example, being serviced by different substations. The different colors represent the different areas. If a fault takes place in one location, we can use the circuit breaker for that substation will usually open, and reclosing operations will take place, and a sectionalizer will try to minimize that portion of the distribution network that is faulted. But
1 minute, Tom.
yes, we're about finished. And so we can begin to manually backfeed to provide power to certain sections that were not damaged by the fault. Trying to do this automatically is the goal, and so we can then begin to close these tie switches between the distribution areas more completely. Okay, so that ends my presentation. So are there any questions?
Thank you so much, Dr. Tom. I think that was very detailed, and yet you touched all aspects of control theory and the architecture. So I think we don't have much room for questions, but we'll ask one question. You know, you in one of your interesting slides where you had the pyramid kind of thing, where going over field devices, substation, remote terminal units, communication, front-end processors, database, SCADA, energy management, right? You know, there is what do you think about, what are the non-operational data? Could you give some examples of non-operational data? You mentioned about some example for operational data, and are we collecting enough non-operational data? You know, if not, what is your perspective on, you know, what should be collected?
Well, non-operational data includes things as your revenue meters. In other words, the energy that has been bought and sold. Now that heads off to the business offices. Or shall we say, relay data that shows successful operations. So these usually go to the post-mortems that the engineering teams in the planning department will use to make adjustments to relay settings, and looking at load levels for expansion of feeder sizes and transformer sizes. That data is also present in the databases, and that's also a particular concern from a cyber standpoint. Even though that data is not used immediately, that gives information to the in the cyber sense to outside players about where load growth is taking place, where one might want to plan a cyber attack. So the non-operational data has a plethora of key informations of where you might want to find weaknesses of the system.
Cool. Thank you so much, Dr. Tom, for your time today, and I appreciate it. I think we're going to move on to the next session. Thank you for your time. And